Hello, today we are going to move on to section 2.2, which is how to add and subtract radicals. So last time in 2.1 we just practiced simplifying them, and today we're going to learn how to add and subtract with them. So let's just review a little bit on the simplifying first, since we still will be doing that as we go throughout the rest of the unit. So I want to make sure you guys feel good about it. Whenever you want to simplify a radical, we're going to reduce the number inside of here. So right now we have a square root. Sometimes you might have like a cube root. So this is a square root, so it's saying what number goes into 27 twice. But 27 is not a perfect square, so it doesn't come out evenly. So instead of doing a decimal, what we do is we reduce it. So we want to think of factors of 27. So like we could do 1 times 27, 3 and 9 would be our factors. We want to pick the pair that does have a perfect square in it. So 1 and 27 is not really going to help me, but if I look at 9, 9 is a perfect square. So that's the pair we want to pick, and I want to think of kind of doing like a little factor tree and reducing this square root of 27 to be a square root of 3 and a square root of 9. And so the square root of 9, since it is a perfect square, we can actually take the square root of it, because 3 times 3 is 9, so the square root of 9 is 3. But then for the square root of 3, 3 is prime, you can't reduce that one anymore, and it's not a perfect square, so it's just going to stay inside the square root. So those are going to be our two parts. To write our answer, we put the whole number in the front, and then the square root in the back. So the square root of 27, we would want to simplify as 3 times the square root of 3. And then let's look at one of these bigger ones. When they have multiple things in them, just break them up and do one part at a time. So I'm going to look at just doing the 54. So if I think of my factors of 54, we could do 1 and 54. There's 2 and 27. There is 3 and 18. And then the next one is 6 and 9. So if I look at those, again, we want to try and pick the one that has the perfect square in it. So far, none of these have a perfect square until, again, we get to 9. So we want to use this pair again. And if you don't have your squares memorized, it would probably be helpful to write a list of your perfect squares and cubes. So this is the one that I made back in 2.1. And so you can kind of go down and see which ones are perfect squares until you have them memorized, and we just use 9. So I'm going to break that 54 to be a square root of 9 times a square root of 6. But then because the square root of 9 is a perfect square, we can actually take the square root of 9, which is 3. So we're going to keep the 3, but then 6 is not a perfect square, so it has to stay inside that square root. And then last time, remember when we talked about having variables, we want to look at their exponent and also think about what type of root it is. So this is a square root, we just don't write the little 2 in it. If it's an even exponent and it can be divided by the 2, it's going to be able to just take the square root by, the shortcut is to take that exponent and divide it by 2. So 4 divided by 2 is 2, and the x squared gets to come out of the square root. But 5 is not divisible by 2, so I'm going to come off to the side here. What we did is we took that square root and think of breaking 1 off so that I can make this into an even number. If I take 1y away, that leaves me with a y to the 4th. But then I still need to keep that other y inside the square root. So now that this one is even though, I can think of that little dividing trick. 4 divided by 2 is 2, so I get a y squared. But then because this is like a 1, a y to the 1, it cannot be divided by 2, so it has to stay in the square root. And so we'd want to do the same thing with the z to the 7. So we want to take 1 off so that I can have a z to the 6, which is an even number, and then leave 1z inside a square root. So if I do 6 divided by 3 or 2, I get z to the 3, power of 3 left over. And then the square root of z needs to stay inside the square root. So now we just put all of our parts together that I've circled here. So everything that is not in a square root, let's take first. And usually we start with a number. So we're going to have a 3 and then an x squared. We have a y squared and a z to the third. And then inside the square root, we'll take everything that was left over. So we have a 6 that was in the square root, and they're all just going to get smushed into one big square root. We didn't have any x's that were left over. We did have a y, and we had one z left over. And so then that would be your final answer once you put it all together. Okay. So hopefully that helps a little bit, refresh your memory from last time. I think we, just for sake of time, let's not do these two and just get into our new stuff. So again, today we're going to look at adding and subtracting radicals. So when we add or subtract radicals, we ask ourselves, how many of this radical do we have? We don't change the actual radical itself. We just add or subtract the coefficients, or the numbers out front of the radicals. So we only add identical radicals. So that means they have to be the same type of square root. We can't add a square root of 5 to a square root of 7. So they have to be the same type of root and the same number on the inside of the root. So here are your steps that you're going to follow. First, you want to simplify if you can, just like what you're practicing. And then we're going to combine the coefficients. Remember, the coefficients are the numbers that are out front of the radicals. So let's start with some easy ones. So on this, it says, what is the simplified form of each expression? And you see that we have this radical, and they're being subtracted. So the first thing you want to look is check that your radicals match. These are both square roots, and they both have a 5x and a 5x on the inside. So that means they're the same type, so we can go ahead and subtract them. So again, we don't do anything with the radical. You're just looking at the coefficient. So this one has a 3 for the coefficient, and this one has a 2. All we're doing is we're literally subtracting those. So 3 subtract 2 is equal to 1, right? So I'm going to have 1 square root of 5x. We're saying I have 3 of them, and I took away 2, so now I have 1 square root of 5x left. And because it's a 1, you really don't even need to write it. You could just say that your answer is the square root of 5x. We don't really technically need that 1 out front. Okay, let's look at another one. So here we're adding this group with this group. If we look, they're both square roots, but this one has a 7 in it and this one has a 5. So we can't add these. Sometimes you might be able to reduce the numbers inside and make it work, but 7 is prime and so is 5. So we can't break the numbers apart anymore. So we can't add. So this would just be your simple form. So that would just end up being your answer. You can't do anything more to it. And then on this one, we look and see that they're both a 7xy and a 7xy, but we have a cube root and a fifth root. So the root also has to match. So because the roots don't match, we can't add them. So roots don't match. So always look to make sure that your root type matches and that the inside of the root, the radicand, is what we call it. Make sure your radicand matches. Okay. Let's try another one down here. So on this one, we have 7 times the cube root of 5 minus 4 times the square root of 5. So we see they're both 5s, but again, this one's a cube root, this one's just a square root. So you can't simplify anymore. So that would be as simplified as you could go. So that would just be your answer. Let's look at this one. I have a square root of xy and a square root of xy. So this one does match. So again, when they match, you can go ahead and just take those front pieces and add or subtract them. So on this one, we're adding. We're going to do 3x plus 4x, which our coefficients would be 7x. So 3 plus 4 is 7. And then your answer, you would just put that in the front now. We have 7x's square root of xy. And that would be your answer. So again, we're just taking those front pieces and adding that part. The square root doesn't change. Okay, those were all easier ones, but sometimes you might have to simplify before you can do anything. So like if I look at this problem, they're saying what's the simplest form of the expression? I have a square root of 12, a square root of 75, and a square root of 3. So right off the bat, you might just say, oh, can't do it. They don't match. But because these numbers can be reduced, we might be able to make it work. So far, all the ones I've shown you on the other ones have all been prime numbers, like 5, 7, where we couldn't reduce them. But 12 and 75, they can be reduced. So if I think of my factors of 12, I have 1 and 12, 2 and 6, 3 and 4. I want to pick the pair that has a perfect square in it, which would be this pair. Okay, so 3 and 4. So I'm going to break down my square root of 12 to be a square root of 3 times the square root of 4. Well, 3 is prime, it can't come out of the square root, so we just keep it. But 4 is a perfect square, so we can take the square root of 4, which is 2. So this is equal to 2 square roots of 3. Now let's look at 75. Our factors of 75, we could do 1 and 75. There's 3 and 15. Those aren't perfect squares. There's 5 and, or sorry, I did that backwards. That was 5 and 15. And this is 3 and 25. No, it's all messy. So 25, though, is a perfect square. So we want to pick this one. So the square root of 75, I can break up to be the square root of 3 times the square root of 25. Where again, 3 I can't break up at all, but 25 is a perfect square. So the square root of 25 is 5. So really, the square root of 75 can be written as 5 square roots of 3. So if I change both of these to their new formats, we have this guy and this guy, my problem if I rewrite it, instead of the square root of 12 is going to be 2 square roots of 3 plus 75, but instead of the square root of 75, I'm going to do 5 square roots of 3 and then subtract a square root of 3. Now they do all match. They're all square roots of 3. So we can go and actually do the addition and subtraction. So that could be a little deceiving at first. When you first see it, you might think you can't do anything. But if they are bigger numbers and you can break them apart and simplify them, you need to do that first to check and see if after you simplify them, will you then be able to do the addition or subtraction. So let's just go in order from left to right. So let's add these two first. Remember, you just take those coefficients. So I have 2 plus 5 is 7 square roots of 3. And then now I need to minus a square root of 3. And this is like a 1 out front. We just don't write the 1. So then I take those front pieces and I get 7 subtract 1 is 6. So our answer would be 6 square roots of 3. So be careful on those ones that have bigger numbers. You might be able to reduce them first and then the problem will work. So let's try this one. Again, first just looking at it, you might think you can't do anything. But if the number can simplify, you want to try. So let's look at our square root of 20. I can do 1 and 20, 2 and 10, 4 and 5. Well, 4 and 5, the square root of 4 is a perfect square. So I want to pick that pair. So that way I can take the square root of 4, which is a 2, and then 5 is prime, so it's just going to stay inside that square root. So that's going to turn into 2 square roots of 5. And then for 45, if I think of a factor pair that has this perfect square in it, 9 is a perfect square and it goes into 45. So 9 times 5 is 45. So for the square root of 45, let's break it apart by doing the square root of 9 times the square root of 5. And since the square root of 9 is a perfect square, we can take the square root, which is 3. And then again, 5 is prime, so we just keep it. So this one turns into 3 square root of 5. Now they have matching square roots, and they're asking us to add them. So our new problem is 2 square roots of 5 plus 3 square roots of 5. So again, you don't do anything to the square root, you're just looking at those coefficients, and we're going to add those. So 2 plus 3 is 5 square root of 5. And that would be your answer. Okay. Hopefully we're feeling okay with that. Let's try just a couple more and then we'll be done for today. So let's try some that have some cube roots on them. So right now they don't look like they would match at all, right? But with cube roots, if you don't have your perfect cubes memorized, that's okay. We don't use them as often. So again, I would have like a list out here where you can look and think what would be a perfect cube that will work. because we want to think what's a perfect cube for 250, not a perfect square. So if I look at my list of cubes, 1, 8, 27, 64, 125, 216 keeps going down. Do any of these numbers go into 250? So I look and I see 125, that does go into 250. 125 times 2 is 250. So let's break up that cube root of 250 as a cube root of 125 times a cube root of 2. So again, you might need to have your list of perfect cubes out because a lot of people don't have these memorized, which is fine. But 5 cubed is equal to 125. So when I take the cube root of 125, I get back a 5. And then 2 is prime. We can't break it down anymore, so it's just going to stay inside that cube root. So this just turned into 5 times the cube root of 2. Now let's look at our 54. So again, we aren't thinking in squares here anymore. We want to think in cubes. So I want to find a number that's a perfect cube that goes into 54. So you have 1, 8, 27, and then anything past that is going to be too big. So 1's not going to help because it's just a 1. 8 does not go into 54, but 27 does. So 27 and 2. So we want to rewrite this as the cube root of 27 times the cube root of 2, where the cube root of 27 is 3. Since 3 times 3 times 3 is 27. And then just like the last one, 2 is going to stay inside that cube root. So now we have our answer for that one would be 3 times the cube root of 2. And then let's break up this cube root of 16. So again, I'm looking for a cube that goes into 16. Anything bigger than 8 is going to be too big. So our only two options are 1 and 8, and lucky for us, 8 does go into 16. So 8 times 2 is 16. So I can break this up as the cube root of 8 times the cube root of 2. Well, the cube root of 8 is 2, since 2 times 2 times 2 is 8. And then 2, again, is just going to get stuck inside that cube root. So this one can be rewritten as 2 cube roots of 2. But now, if we looked at it originally, none of these matched. So we could have just said, oh, can't do anything, and then gone on our way. But we would have been wrong, because if I simplify it, now they've all turned into cube roots of 2. So I can do my problem. So let's rewrite it. Kind of running out of space, but we have, instead of the cube root of 250, I have a 5 cube root of 2 plus a cube root of 54, which I'm going to write as 3 cube roots of 2, subtract a cube root of 16, which I'm going to do as 2 cube roots of 2. So we're going to ignore the cube root of 2 part, and we're just looking at those coefficients. So let's just kind of do it in our head. 5 plus 3 is 8, and then 8 subtract 2 is 6. And then we just keep the cube root of 2 on the back. So our answer would be 6 cube root 2. Okay. So let's try another one. This one's almost exactly the same as the one we just did. We've got a cube root of 54, cube root of 54, cube root of 16, cube root of 16. They're just asking us to add it instead of subtract it. So we already did the work for that. Cube root of 54 we know breaks down to 3 square root of 2, 3 cube root of 2. And 16, the cube root of 16 we already did. We know it equals 2 cube roots of 2. Let me write that a little bigger. 2 cube roots 2. And they're asking us to add them this time. So just take those coefficients, the 3 and the 2. 3 plus 2 is 5. And then keep the cube root of 2 on the back. And that's your answer. So that was kind of easy because we already did the work up above. Let's do this one. This will be our last one. We've got 3 cube roots of 81. Subtract 2 cube roots of 54. So on this one, they already have the numbers in the front. So far with our cube roots, we haven't had any numbers in the front. We've just looked at the roots. So we need to be careful that this one had a 3 and this one had a 2 already to start with. But let's go ahead and break up this cube root of 81. So we want to find something that goes into 81 from our list of perfect cubes. So we have 1, 8, 27, 64. One of these needs to work. So 27 is actually going to be the one that works. because 27 times 3 is 81. So we're going to use that one. I'm going to do the cube root of 27 times the cube root of 3, since 27 times 3 is 81. Well, since 27 is a perfect cube, the cube root of it is 3. And then that 3 cube root of 3 is just going to be stuck in there since 3 cannot get broken down anymore. So we're going to rewrite that as 3 times the cube root of 3. Now let's look at our 54. We already know that the cube root of 54 is from up here. We already did it as 3 times the cube root of 2. So if you want, you can just break that down. And we know that it's going to be 3 times the cube root of 2. So we don't have to redo our work there. Here's the thing that a lot of students would forget though. Remember, this one had a 3 to start with and this one has a 2 to start with. We can't just drop those. Because when I did this, I got a 3 out front, but this 3 is different than the 3 that I started with. So I need to bring this 3 down and they end up getting multiplied. So I get 3 times 3, which is 9 cube roots of 3. And same with this 2. I need to bring this 2 down so that I get 2 times the cube root of 2. Well, 2 times 3 is 6 cube root of 2. So our new problem, if we rewrote it, originally it was being subtracted, we would take the 9 cube root of 3 and we would subtract 6 cube root of 2. So we still can't actually do the subtraction because these cube roots have different numbers on the inside, but it now is at least in simplified form. So we simplified it, but we couldn't actually do the subtraction since this one has a 3, this one has a 2. So that's as far as we can go. But just be careful with that. If they start with that number in the front, you need to make sure to bring it down and times it to be a part of the new coefficient. Okay, so that is adding and subtracting your square roots and cube roots. Hopefully you guys feel okay with that. If you guys have any questions as you go through your homework, as always, please reach out to me and I can either help you on Zoom or answer through email, but I am here to help. Hope you guys have a great day. See ya.